Yeah, welcome to this lesson. In this lesson, we'll be treating electronic configuration. Yeah, electronic configuration refers to the arrangement of electrons around the nucleus. So when you hear the word electronic configuration, you're talking about how electrons are being arranged. In our previous lesson, we talked about how every atom is made up of a nucleus and an electron, basically. So, and these electrons are seen to revolve around this nucleus at specific distances. So this arrangement at specific distances is what is known as the electronic configuration of that particular atom. So these arrangements follow specific rules based on energy levels and sub-levels, and it influences this electronic configuration influences elements properties, their chemical properties, and also their reactivity. It also influences stuff like their bonding behavior and also the placement in the periodic table. Let's go forward into some of the rules that are governing electronic configuration. So among one of the first rules we talk is the rule that involves the energy levels. So electrons flew from lower energy levels to higher energy level. We will see later on the rule that actually tries to explain this particular sentence. Also, there is also what is known as sub-levels. So energy levels are also divided into, we have energy levels, and we said electrons flew from lower energy levels to higher energy levels. So now these energy levels, each of these lower, higher energy levels, they have what is called sub-levels, and these sub-levels can be divided into four different groupings, and they are S, P, D, and F. So there is a principle, one of the principles we'll be talking about basically, that is responsible for the electronic configuration and the arrangement of electrons around the nucleus, is called the Pauli's exclusion principle. So in this principle, it tries to talk about how each orbital holds the maximum amount of an electron of opposite spins. And also another rule is the Horn's rule, which talks about how electrons occupy orbitals singly before pairing up. So let's see what majority of these rules are. So we'll be going into a deep dive. So but before then, we'll talk about energy levels and sub-levels. So electrons occupy energy levels or shells. So when you hear the word energy levels, they're talking about the different electron shells where electrons are found. So these shells are designated by a principal quantum number, usually an integer, being represented with the letter n, and it could be 1, 2, 3, 4. They represent integer numbers. So each of these energy level contains individual sub-levels. So these individual sub-levels are always S, P, D, and F. So and these sub-levels, they define the shape and the number of orbitals that are present in each of these energy levels. So these orbitals represent regions where electrons are most likely to be found. As we said earlier, that this is what is the basics for electronic configuration. So and the number of electrons in a sub-level the number of electrons that sub-levels can hold are usually static, and each of these sub-levels, they have their individual number of electron, maximum number of electron that they can contain. So like the s orbital, it has a maximum number of 2, the p orbital has a maximum number of 6, the d orbital has a maximum number of 10, and the f rather, has a maximum number of 14. So these numbers are constants and they remain the same throughout. So let's see these principles. So I listed out here three principles, three basic principles, and these principles are the Aufbau's principle, the Pauli's exclusion principle, and the Horn's rule. So these principles are like the fundamental guidelines that ensures that electrons are occupying the necessary orbitals in the around the nucleus. So let's talk about the Aufbau's principle. So the Aufbau's principle states that electrons occupy the lowest energy level first, the lowest available energy level first, steadily filling the orbitals from ground state upwards. So this principle is just trying to explain that when electrons are trying to fill orbitals around the nucleus, that they will start from filling the lowest available energy level first. They will first start from filling the lowest available energy level. That's the energy level with one. After the energy level of 1 is being filled up, the next they will fill up is the energy level of 2, and so on. So, and they do this steadily. So this is the basics of this Aufbau's principle. So let's go on to the next principle, which is the Pauli's exclusion principle. So this principle, on the other hand, tries to dictate that no two electrons in an atom can have the same set of quantum numbers. So when we go on to what quantum numbers is, I think this particular principle will become clear. But let me just give a brief summary on what quantum numbers try to entail. So quantum numbers are like designations to electrons, So, and each of these each electron have their designation, and their designation is kind of like a kind of level of ID, which this Pauli's exclusion principle is trying to state that that there is no two electrons that can have exactly the same set of quantum numbers. So no two electrons will have exactly the same set of quantum number in a particular atom. So maybe this is like the basics for this exclusion principle, and this principle tries to restrict that electrons should maintain their identities throughout the space around a nucleus. So the rule simply just tries to say that is the simplicity of the rule is just trying to say that each electron that is around a nucleus are identical. That they are not identical, rather they have a unique identity, and this identity is represented by their quantum number, the sets of their quantum number. So when we go into quantum number, I believe it to become clearer. We have different quantum numbers. We have the principal quantum number, the spin quantum number, the magnetic quantum number, and the azimuthal quantum number. But later on, we would see what these quantum numbers entail. So now let's move on to the final rule, which I stated here, which is the Horn's rule. So this rule is the rule that governs the way electrons fill orbitals. So, and the rule tries to explain that electrons will first occupy the orbitals singly before they try to then pair up. That's what this principle tries to talk about. It says when we have an orbital, probably let's say a 2s orbital, said, oh no, let me use orbital that has more than one space. Like we have a 2p orbital. It said before these electrons would start pairing up, because in every orbital, in every space in an orbital, there is always a pairing up of electron once they are trying to fill up the electron or the orbital. So before these orbitals fill up, they would first enter each of the before these electrons fill up, they will try to enter each of these orbitals one after the other. So once they fill in singly, the next they will do is they will start pairing up after them. So this is what this Horn's rule tries to state. It tries to say that every orbital will be filled up singly first before they are being paired up, before the electrons in this orbital that have been filled will become paired up. So all these principles and rules together, they are what are responsible for the electronic configuration and the arrangement of electrons around the nucleus. Let's move on. When you try writing the electronic configuration, it's important for you to know that you would write electronic configuration first by indicating the energy level, next the sub-level, then next the number of electrons that is present in that particular orbital or in that particular energy level. So as I said, we have the s orbital, the s energy level, the s sub-level rather, it has a maximum of 2 electrons that can be in it. The p sub-level has a maximum of 6 electrons that can be in it. Then the D has a maximum of 10, the F has a maximum of 14. So for writing the electronic configuration, you will start from the lowest. So we'll first start from the 1s. So the 1s, 1 is representing the energy level. 1 is representing the energy level. That is the n which I stated in the time when I was at the point when I was defining what the energy levels are. 1, 2, 3 behind all these numbers are representing the energy levels. After you've written the energy levels, next you write is the sub-level. That's the S, P, D, and F. Then after that, you then write the number of electrons that are present as a power. So this is how we write electronic configuration of atoms. So this notation helps to visualize the electron distribution and predict chemical behaviors. So the configuration can be also be represented using orbital diagrams. It can also be represented using orbital diagrams. So let's move on to what we have next in this lesson. We have to talk about the valence electrons and also the periodic trends. So what are valence electrons? Valence electrons are those electrons that are at the outermost shell of an atom. So they are the outermost electrons in the outermost shell of an electron. So from how I wrote it here, I said valence electrons are the outermost electrons and are primarily responsible for the chemical reactivity of every atom. So elements in the same group have similar valence electron configuration. So when you have elements in the same group, remembering our periodic table, when the elements are in the same group, they would have the same number of valence electron in their outermost orbital. So this is the reason why sodium, potassium, and also sodium, potassium, and strontium, they have the same number of electron in the outermost orbital. So they have an s orbital as their outermost sub-level of orbital, and in each of these orbitals they are always having 1 electron at max. in that last orbital. So for lithium, we would see it is 1, it would have the 2s 1. For sodium, would have the 3s, would have a 3s 1. For potassium, would have the 4s 1. So this is how they are being arranged. So explaining their similar these number of electrons, these valence electrons are responsible for the chemical reactivities, and the electronic configuration can be used to predict the periodic trend of atoms in the periodic table. So let's go on to some of the exceptions that violates this arrangement of electrons in electronic configuration. So some elements, especially transition metals, there is a bit exception to the typical electron filling. So according to normal Horn's rule and the Horn's rule, the Aufbau's principle, and the rest, they say normally they're supposed to fill from lowest to highest, but there's some elements or group of elements that seem to make an exception to these rules, and these elements specifically are called the transition metals. So in case you see in questions where they say which elements are known to violate the normal rules for electronic configuration, these elements are known as the transition elements, and they exhibit exceptional properties by trying to deviate a bit from the normal rule that govern electronic configuration. So for instance, we have chromium and copper. These species, they tend to fill in a different manner. Like how we can see here, we see normally this is the electronic configuration. According to the normal rule, it's supposed to fill their outermost electron in this order here. Supposed to fill in this order. AR, that's representing the highest filled orbital, 4s to 3d4. This is supposed to be how it is written, but for some reasons, because they're trying to attain partial stability, they fill in this manner. Instead of the 4s2 to be filled first, you'll see something like this here. You see this here, the 4s, instead of the 4s to be filled completely, it will prefer filling the 4s half and filling the 3d half. So 3d is supposed to take a maximum of 10. So they would prefer filling the 3d half, making it 5, and 4s is supposed to have a maximum of 2. Then it's prefer filling the 4s 1. That's both of them would have partial stability, partial filled. They are partially filled. So this same thing happens in copper. Copper supposed to have 4s to 3d9, but because of it prefers to fill partially or even fully, it will prefer to give the 3d orbital a 10. That's what we can see here, and have half configuration in the 4s. So you can see something like 4s1 3d10, where this one will be full and this is going to be half. So it prefers to favor these ones that are more, filling them partially more, comparing it to the ones that are less. So these are some of the exceptions to the rules that govern electronic configuration. So in conclusion, electronic configuration is a fundamental concept that tries to connect atomic structure with chemical behavior. And by understanding this, they can tell you how electrons are arranged, and chemists can use it to predict elements reactivity, bonding pattern, and formation of molecules. So it also provides a basis for understanding the structure and organization of the periodic table. So that will be all for this lesson. Goodbye.